Hey everyone, let's do another work energy principle problem. A 258 kilogram load is lifted 20.0 meters vertically with an acceleration a equals 0.160 g by a single cable. A, determine the tension in the cable. B, determine the net work done on the load. C, determine the work done by the cable on the load. D, determine the work done by gravity on the load. And E, determine the final speed of the load, assuming it started from rest. Okay, so let's take this one piece at a time. Let's start with A here. Okay, the first thing we want to do here is draw our free body diagram. We've got a load being lifted vertically by a cable. So the only forces acting on that load are going to be the tension due to the cable going up and the force of gravity due to its weight going down. Okay, so that's it. That's our free body diagram. Okay, so we want to assign a positive direction to this as well, since there is motion, and that motion is upwards. So I'm going to let positive be upwards. It really doesn't matter what direction you pick. It'll work out regardless. Okay, so I have to find the tension in the cable. So let me start with Newton's second law. F net, and I'm working in the y direction, equals MAY. Okay, so my net forces can be broken down into FT and FG. And since FT is in the positive direction, I do FT minus FG equals MAY. All right, so now since I'm trying to find tension, I'm going to isolate for FT, add FG to both sides. And you know what? I'm just going to go ahead and skip a step here, and I'm going to replace FG with MG. Okay, so then you get FT equals MAY plus MG. Okay, so factor out the mass now. So you get M bracket AY plus G. Now plug in your numbers. Okay, so the mass you're given in the problem is 258 kilograms. The acceleration in the y direction we're told is 0.160 g's. Okay, so 0.160 g plus g. Okay, so here we've got 0.160 g plus g. If you add those two together, you're going to get 1.160 g, right? Because there's an invisible one there. So you're adding these two numbers together. Okay, so 1.160 g. So the next line I'm going to just write exactly what it is we're calculating. 258 times 0.16. Sorry, that should be 1.160. So times 1.160 times g, which is 9.8 meters per second squared. Okay, so when you multiply all these values out, you're going to get a force of tension of 2.93 times 10 to the 3 newtons. And it is accurate to the correct number of sig figs 3. Okay, so there is the answer to part A. So we are 1/5 of the way down the question. All right, part B. Determine the net work done on the load. Now, whenever you see net work, you should think net force. Okay, the reason for that is because when you look at the formula for work, okay, so we know that work is equal to force times displacement times cosine of the angle between the two. Okay, so if we're doing net work, then we have to use net force. So net force times displacement times cosine theta. Okay, so take a look at our free body diagram from part A. Okay, so our net force has to be going up. Why? Because the object is moving up. It's accelerating up. So this is the direction of our net force. And at the same time, it's moving up. So our displacement is also up. F and D are in the same direction. Therefore, theta is 0 degrees. And we know that cosine of 0 is 1. So this thing disappears, and you can write a 1, or you can just not write anything. Okay. Net force, you can replace net force with mass times acceleration in the y direction, because that's what it is. Okay, so here we go. MA, now AY we already know. It's 0.160 g. Okay, so you know what? Why don't I do one more line so I don't jump too many steps. So we do MAY delta D. Now, AY is 0.160 g. Okay, so I'm going to put 0.160 and then G, and I need an M, and then there's D as well. So all these things are getting multiplied together. So here we go. So then we get 0.160 times G, which is 9.8 meters per second squared, times the mass, which is 258 kilograms, times D, it's lifted, let me bring this down, it's lifted 20 meters. Okay, so that's our distance. So just let me fit that in there, times 20 meters. I'll multiply that through, and when you do, you are going to get that the net work is 8.09 times 10 to the 3 joules. Okay, so there's your answer for part B. Okay, net work requires net force. Okay, so we're making pretty good progress right now. C, determine the work done by the cable on the load. Now, the effect of the cable is that the cable is causing tension, right? Because the object is going up. So pretty much we have to find the work done by tension. Now, because net work is found by net force, the work done by tension is going to be found by the force of tension. So that's where you're going to have to plug in here. Okay, so let's do part C now. Determine the work done by the cable on the load. So for part C, the work done by the cable is equal to the force of tension times the displacement times cosine of theta. And just like in the previous part, remember the angle between the net force and the distance, or in this case, the tension force and the distance, it's still 0. Theta is still 0, so cosine of 0 is 1. So that's nice. That simplifies out. Cosine of 0 degrees is equal to 1. So that disappears. You can just not write it. Okay, so now we get force of tension. We just found it in the previous part. It's 2.93 times 10 to the 3 newtons. 2.93 times 10 to the 3 newtons. And all you have to do is put in the displacement, and it's going up 20.0 meters. Multiply those two numbers together, and you are going to get 5.86 times 10 to the 4 joules. So that is your work done by the cable on the load. So there's your answer to part C. So you can see it's not too bad. It's a 5-part question, but it goes by pretty fast. Okay, let's see. Part D, determine the work done by gravity on the load. Okay, so that's pretty straightforward. We're just gonna plug in Fg as our force. Okay, so the work done by gravity, let's choose a different color here. Part D. Okay, the work done by the force of gravity is equal to the force of gravity times the displacement times cosine of theta. So now this is where it's a little different. Okay, so remember we have our object. So you've got your force of tension going up, you've got your force of gravity going down. So take a look at this. Your force of gravity is going down, right? That's your Fg, but the displacement is going up, right? So now the angle between these two vectors is 180 degrees. Okay, and cosine of 180 is -1. Okay. So let's, you know what, we can actually do that right away. So Fg is mg, so mg delta d, and we put that minus in front there. So just plug in your values. Okay, so equals -258 kilograms times 9.8 meters per second squared times the distance. It's still going up 20 meters, so you're going to multiply that by 20 meters as well. Okay. When you plug those three numbers in, multiply them all through, you're going to end up with -5.06 times 10 to the 4 joules. Now, before you think you did something wrong because your work is negative, that's actually perfectly all right. In fact, it's accurate. Gravity is slowing it down, so the work done by gravity is negative. It's not helping it do what it's trying to do, which is go up. So we give it a negative sign, and that's how it worked out. So last part, determine the final speed of the load assuming it started from rest. Okay, so now we're doing almost like a kinematics thing, but since, you know what, since we're doing work energy problems, let's solve it using the work energy principle. Okay, so in order to use the work kinetic energy theorem, you're using net work. So net work is equal to the change in your kinetic energy. And at the same time, we know that our initial speed is 0 because we were just told that in the question, and we need to find the final speed, v. Okay, so delta EK, you can rewrite it as 1/2 mv squared minus 1/2 mv naught squared. Final minus initial, right? And that's equal to the net work. So let's see. V naught is 0, so that helps. So if this is 0, 0 squared times anything becomes 0. This whole expression disappears. Okay, so net work is 1/2 mv squared, and we are looking for that v. So let's just isolate for that right now. We're going to have to multiply the 2 across, so it's going to be 2w divided by m, and then you square root the entire expression. So v is equal to 2W net over mass square root. Now, if you have to do that in a few steps, that's okay. You should do it like that until you start becoming more confident with how fast you can actually isolate variables in a formula. Okay, so now plug in our values. We already found the net work in part B, so I'm going to use that value, 2 times 8.09 times 10 to the 3 joules, divided by the mass, which is 258 kilograms. And take the square root of that, you are going to get the speed is 7.92 meters per second. And that's it for this video, guys. I hope you enjoyed it. Please smash that like button so I can know if you guys are actually learning things from these videos. And if you do have any questions, be sure to leave them in the comments section below. All right, guys, I'll see you in the next video, 105, Potential Energy 1. Hey, guys, welcome to the end screen. Woo, I got you guys. All right, here's what I need you to do. Subscribe to this channel. Okay, I'll stop. Thank you guys so much, as usual, for watching. If you guys enjoyed this video, be sure to subscribe to my channel by pressing the red subscribe button below and smash that like button so that I know what I'm doing makes sense to you guys. First face reveal I do and my hair is all frizzy. I post new videos every weekday at 12 noon. Finally, guys, I love you so much for watching. Please continue to do so every weekday at 12 noon.